been a while. Let's see. Oh, shoot. You know what? I hope it. Sorry. I realized my computer's on mute, so I couldn't hear if anybody said good morning or said something. I'm sorry. I missed it. Sorry. Anybody ask a question that I missed? I'm sorry. Okay. Sorry about that. I think I was in a meeting a couple days ago and I didn't want my computer to make noises and interrupt. So I turned the, I put it on mute, which probably should have stopped putting it on mute when I got done, but yeah, that's neither here nor there. So new activity today. This one, it's going to be, this is kind of a little different now. I think I said that, week 1 and week 2 were more just, here's a big random assortment of algebra topics that we're going to review. And there wasn't a lot of you trying stuff. It was mostly just explaining, just because there's a lot to go over. So we wanted to shove it all into the time we had. But now it'll be more, kind of focused on one part of Math 111, getting ready for it. Because Math 111, there's so many topics in there and it moves so fast that, there's not a super lot of time to do a lot of the explanation and the leg or the groundwork before the actual topic we're talking about. So yeah, it's kind of nice. This class, we can kind of just in time for Math 111, we'll kind of catch up. So this one, we're going to talk about investigating composition and inverse functions. What does that mean? And what is it kind of the background behind it? Because in Math 111, when we do section 2.6, you might have already done it if you're ahead, probably, I don't know. But if not, it's kind of the Math 111, we only kind of had time to say, okay, here's how you do this process, but not really the why and I don't know, it's hard to understand something when you don't know why you're doing these steps, and hopefully that makes sense. Yeah. So that's what we're going to do today, is just kind of building our understanding of what we're trying to do in that section 2.6. And then I think it'll make it easier when we actually go and do it. But I'm going to try to find it and link this PDF in the chat. It's in Canvas in week 3 module now. I just put it in there yesterday, I think yesterday afternoon, but maybe I can just put it in the chat here in case you want to open it. Dang, where is it? Week 3. This is week 3. Sorry, here he goes. Okay, sorry. Took a while. I think I need to organize my stuff better. Okay. I think it should be, so it should be in the chat now, in case you want to open it. So I think what we'll do is we'll kind of, go over a lot of this together. And there's a lot of examples of the same type. So maybe we'll go over, most of them just as kind of as a class, and then we'll kind of break into groups and then have you guys try 1 or 2 and just comparing with your group members and stuff and discussing stuff. I think that really helps, because sometimes there's someone who's super understands it and then another person who doesn't understand it, and they get together and it kind of it's explained in a different way maybe than I could do, and it makes more sense. So I think that'll be good. Yeah. Okay. All right. Let's see. Any questions though before we just get into it? Any questions about anything like the class in general, or what's going on in Math 33 or Math 111 or extra credit stuff? Well, feel free to stop me, please. In the chat, say something, or just unmute yourself or raise your hand, and I'll try to answer any questions. But depending on how long this takes, maybe we can even leave time at the end for some factoring stuff. Just, if you have any questions or any examples you want to go over, or talking about certain factoring technique that you're not sure about. Okay, I think it looks good. So we'll just kind of read over it together and see if we can go over some examples, and then save some examples for when we get into groups. Okay, so in this activity, we will write functions for simple operations and then investigate how more complicated functions can be built from these smaller functions. So it's really like combining, they call them the composition of 2 functions, but it's you're taking 2 functions, say one function takes your number x, whatever number you give it, and it adds 2 or something. So it could, your function might look like, just as an example, f of x is whatever number you give it x, I'm going to add 2 to it. That's the first function. And then the second function, maybe it takes x and divides it by 5 or something. If I want to combine those functions, maybe I want a new function that does both of those things. I want to take any number x that's given to me, and I want to add 2 to it and also divide it by 5. That's what really the composition of functions talks about, taking 2 functions and combining them. So I have a new operation that does multiple things. So that's the idea behind composition. And they write it, it's kind of strange. It looks like FOG. It looks like fog of X, but really it just means combine them together. Composition. Oh, yeah, it would be like you're taking the division operation and the addition operation and putting them together. That's the idea behind composition. So we look at that in section 2.6 and maybe 2.7 as well, I think. And then the other part of it is the inverse. We'll talk about inverse functions. And just to get an idea of it, before we tackle it, if you had a function like f of x, say, okay, like maybe the same one, x plus 2, the inverse of that is just think, what operation is f doing? I want the opposite of that. So f itself is taking your number that you give it, x, whatever it is, and adding 2. The inverse would be, I'm going to take your number and subtract 2. That would be just the opposite operation. So that's really the idea behind the inverse. Yeah, composition means I take two functions and combine them so that my new function does multiple things that those two functions did. Inverse is just the opposite. I want my new function, the inverse, to do the opposite operation or operations as the original. And that's really it. I think to me, I don't know if it's true for everybody, but the hard part for me was the notation. Like for the composition, they wrote f of g of x. When I see that, do I think the word composition? I don't think about composite. I don't know. It's hard to remember that, I think. F of g, I call it. Anyway, that's weird. And then for inverse, it's written, okay, if I have a certain function like the original guy, f of x, and I want to find its inverse, I write f with the little -1. It almost looks like an exponent, like you're raising something to a power, but you're not really doing any operations. It's just purely notational. I write f little -1 exponent or superscript of x. That means the inverse of f, inverse function. So it's super confusing. Yeah, because I always think that, that I'm doing some kind of operation. I'm raising something to a -1 power, but that's just the way you write it. And if I look at that, I just read it as f inverse of x. And that would be what I would call the title of the inverse function. So I think a lot of times in math, that's the hard part. If I can just wrap my mind around how to write things and what all the symbols mean, then I think you're okay. But that's the hard part for me, is always, can I wrap my mind around all these weird concepts? Well, I don't know if that's true for everybody. So those are what we're kind of focusing on in this one. And if you get to the section when we talk about inverses, you might have already gotten there, maybe not. Don't worry if you haven't. It just kind of says, okay, step by step. If you're given a function, no matter how complicated it is, it could have a lot of things going on. This is how you find the inverse. You do step 1, step 2, and it doesn't really give you the why you do it, and also what really is an inverse. What are we trying to find? There's not enough time, I guess, in Math 111 to give us the motivation behind what we do. So it's kind of what we'll build on today. I think if you know what an inverse function is and why we might want it, then it'll help you find it, I think. Yeah. So anyway, that's a lot of talk. Let's just keep going, huh? Simple operations of addition, subtraction, multiplication, and division of two numbers are functions. So if you've seen functions, chapter 2 kind of talks about them in so much detail. I never want to hear the word function again in my life. If I ever hear someone say that, I'm going to punch them in the face. I'm tired of that word. No, don't do that. But when one of the two numbers in any of these operations is fixed, the operation can be expressed as a function in one variable. All right, well, that's just, they're saying something in a different way that we said. Just these examples over here, f and g, those are functions. For example, adding 6 to a number x can be written as, f of x is x plus 6. So similar to what we wrote, but we wrote x plus 2. So first we're going to just practice, let's see, these examples. So maybe we'll do, a few of them just out loud. We'll go over them. And then maybe a few you can try on your own, and then we'll get back together and see if we all get the same thing. But they just want us to write a function notation for it. They're going to describe what it does in words, and we're going to write it in math symbols. So for example, the first one says, I don't know, can you see it pretty good, even though it's small? Maybe we can focus in on it, huh? The function g. Okay, so they gave it a name. I don't want to write f of x. I want to write g of x, just because that's what they told me to call it. Okay. It adds a number x to 2. So I guess with that one, the question is, okay, the way they phrased it, it adds an x to 2. It kind of sounds like they want me to go 2 plus x, or is it going to be x plus 2? That's kind of the tricky question. let's see, I go, is it gonna be 2 plus x or x plus 2? Well, the good news is with addition, we're adding, it doesn't really matter what order to, you know, when you add two numbers, well, does it matter if it's 5 plus 2 or 2 plus 5? Either way, you're gonna get the same answer, so it doesn't really matter. But if this were subtraction, if they had said a function g subtracts a number, then it does matter, right? If I have 5 minus 2, that's different than 2 minus 5. You're going to get a positive or a negative. So just because I want to get in the habit of writing things in the correct order. I think with the way they're phrasing it, g adds a number to 2. That kind of sounds like 2 was already there, and then I added the x afterwards. So I think you want to put the x on the right side. But if they had said it backwards, if they had said the function g adds 2 to a number x, then that sounds like x was already there. Then I'll put plus 2 afterwards. So like I said, in this one, it doesn't actually matter. That would be a correct answer, or the other way, just because of the way addition works. It doesn't matter what order the two numbers are in. But just because, yeah, we want to get in the habit of putting things in the order that they give it to us, because it does matter with multiplication or division or subtraction. So it's probably better to write it in the way that we circled than not. Yeah. Okay. So what do you think? Any questions about that, or does that kind of make sense? Yeah. I don't know if I were, if I was just given this worksheet as a student, I might not know exactly what they're asking me to do, but then maybe once I see an example like that, I'd say, oh, okay, that's what they're asking me to do. Okay, I think I get it. So then how about for number 2, h? Okay, they're saying the function should be named h. All right, I'll call it h of x, because that's our variable. It subtracts 5 from a number x. So what do you think? Should it be x minus 5 or 5 minus x, the way they phrase it? What do you think?
Yeah, exactly. And talk about
X minus 5.
Yeah, I think you're right, huh? Yep. It subtracts 5 from a number x. So yeah, the way they phrase it, it sounds like x already existed, and now I'm subtracting 5 from that. Yeah, and like I said, in that one, it would matter. Yeah, nice. Yeah, it would matter the order. If I put it the other way, it would be wrong, because x minus 5, 5 minus x, they're almost the same answer, but one will be a positive and one will be a negative. So it would matter. Okay. So I think that's maybe just the difficult part, going from words to math symbols or numbers and addition signs and all that. All right, so far so good. How about number 3 says the function j, okay, I guess you don't see a lot of, most functions are either f, g, maybe h. You don't see j too much, but you see it when you've kind of exhausted all the other names, f of x, g of x, h of x. Okay, let's try j now. Subtracts a number x from 5. So how about that one? Is that going to be the same as number 2 or opposite?
Opposite?
Yeah, nice. Subtracts a number x from 5. It makes it sound like 5 was already there and you're putting a minus x on it. Yeah, you're right. Nice. Because it is phrased kind of the opposite way of number 2. Number 2 said subtracts 5 from x. This one says subtracts x from 5. And those would be different answers. Those 5 minus x, x minus 5. Yeah, that's one of the hard things in math, I think, is translating from words to symbols. That's why word problems or applications are so difficult. Usually it's just, how am I going to take these words and make them into symbols? I don't know what the heck I'm doing here. All right, I think so far so good. Okay. Let's see. Number 4 says the function k. All right, I guess we're running out of letters, so I'm not calling this f of x. I'm not calling it g of x. I'm calling it k of x. Just going through the alphabet. Multiplies a number x by 3. So that one, do you think it looks more like 3 times x with 3 on the left, or x times 3 with 3 on the right? Multiplies a number x by 3. Do you think it's one or the other, or does it really matter?
I think it's the first way.
Yeah, I think it's kind of tricky because with multiplication, it doesn't actually matter. So the way they say it, it multiplies a number x by 3. I almost feel like it sounds the way they phrase it sounds more like x times 3, like kind of like where we said x already existed and then you subtracted 5, like in number 2. It seems like in this one, x already existed and then you multiplied by 3. So I think I would start like this, but you never see that, right? A variable on the left and a number on the right. If someone said, oh, x times 3, you would simplify it to just 3 times x. So I think in this one, it's kind of like addition, where if you're taking 2 numbers and you add them in this order or the opposite order, it doesn't really matter. So the answer for number 1, either of those is correct. It's just And, like I said, I would prefer the top one only because it's getting us ready for the times where it does matter what order we're in, like in number 2 and number 3. But in number 4, multiplication is a lot like addition, where it doesn't matter really what order they're in. So I think either one's right, but only because you never see a variable on the left and the constant on the right. You'd probably simplify it to 3x. But I think the way they phrased it, I would start with x times 3, x on the left, 3 on the right. But yeah, just to simplify, because 2 numbers multiply, it doesn't matter what order they're in. It's just, I would like to see the constant coefficient on the left. It looks more natural, or more what we're used to. So that might be something good to keep in mind, that when I'm adding 2 things or multiplying 2 things, the order doesn't matter. So I'm free to go either way, whatever I want. But subtraction and division, it does matter, because subtracting numbers one way versus the other way, you're going to get a negative or a positive. Switch the sign. Division would matter too. If we had like 5 divided by 10, that simplifies to a half. But if I had it upside down, 10 over 5, that's actually 2. So they're definitely different numbers. That's a half, this is 2. So with subtraction and division, it does matter what order, that they're phrasing it in. But yeah, so anyway, that's a lot of talking for just saying on number 4, either way is right, but I would probably just write it as 3x, because that's how it looks nice and we're used to that. Okay, so far so good. I think we're doing good here. Number 5 says the function capital F. Now I think they're running out of just regular alphabetical names, and now they're going to capital. Okay, whatever. Function capital F divides a number x by 4. Okay, now we're dividing. So do you think it's x over 4 or 4 over x, by the way they say?
X over 4?
Yeah, I think you're right, huh? Good call. And then someone in the chat said, yeah, x over 4. If they had said it divides a number 4, or it divides 4 by a number x, then it would be the other way. But you're right. The way they say it, it's like x existed already, and then you are dividing it by 4. So 4 should be on the bottom. All right. And then in that case, yeah, it does matter. It does matter what order. So subtraction and division does matter what order. Okay. So that second one's not right. Okay. So far we're doing good. All right. How about then number 6 says the function g. All right. We already used lowercase g, so we're moving on to uppercase because we're running out of names for this thing. G of x. It divides 4 by a number x. So how about that one? How would that look?
4 divided by x.
Yeah, you're right. That one I know. Probably no one answered because they're like, okay, this is pretty obvious here. No, they phrased it the opposite of number 5. Is this number 6? Yeah, number 5 said divides a number x by 4. So x was already there. You're dividing by 4. This one says it divides 4 by a number x. So it sounds like 4 was already there and you divided it by x. Yeah, and I don't know why I wrote that one kind of sideways and the first one vertical. I should just write it regular. Yeah, with 4 over x. Let's see, 4 over x. And one thing I would mention is that in number 5 and 6, they say it divides something by another. So you could, if you wanted to, write, number 5 as x divided by 4. But you never see a function that looks like that. Here's a function. Let's do something with it. It looks like a number x divided by 4 with a division sign. You don't really see that very much. I think kind of like once you leave arithmetic pre-algebra and you move on to algebra and pre-calc, you'll never see a division sign ever again. They just always write it as a fraction. So even though technically the way they phrase it, it seems like it would be x divided by 4, and then number 6 would be 4 divided by x. We never write that because it's equivalent to this fraction, and so it doesn't seem like it, but fractions are usually easier to manipulate and deal with, especially when you're combining them with another function. We kind of know how to deal with them combined with another one easier than if they were written in division with actual division sign. So I don't know if I was wondering about that. But
Would we get the answer wrong if we put it in the division sign, then fraction?
That's a good question. If it was on like a midterm, where I grade it, I would say I would give you full credit. But I think maybe on the homework, they might say, their classic, what do they say? Although it's the right answer, it's not simplified or it's not in the right form or something. So they would say, you're right, but we want it in this other form. So yeah, the answer is kind of complicated. I think I'm fine with it. I'll mark you correct and stuff. Yeah, but the homework might say, although it's correct, it's not simplified. Makes you want to punch your computer, but no, I paid a lot of money for this computer, so I can't. Anyway, good question. No, yeah, it's hard to say which way they want it sometimes. Oh, let's see. And then these next couple problems, now they're just it's not going to be just adding or subtracting or multiplying or dividing as our answers. We might have more things going on, like square. What does that mean? So for example, yeah, number 7 says, okay, they're going back to the name f of x. Okay, I guess we're starting over. We imagining we didn't use these letters yet. It squares a number x. So what would that look like? Does that mean I put x inside of a square like that? Okay, silly, right? Okay, what do I do to x though? What does he need? What do I need on the right side besides just x? Is that a silly question? Maybe. Oh, let's see. Someone said, yeah, nice. X to the, sorry. What were you going to say? Sorry. Oh. Okay, in the chat, someone said x to the second power. Yep. And I think, you know, when you're chatting, it's hard to tell what, you know, it's hard to do an x to the second power. So I think usually you'll see it as x. That's how it was written in the chat. That usually means when you see that to the power of, but somehow when I'm typing, I don't have the capability to write that. So that's one way you could write it. But yeah, in the homework, you know, you probably write it as x with the exponent of 2. Nice. Okay. So it definitely helps to know all the phraseology or whatever, the square, what does that mean? And then how about then number 8 is they're calling it g. So I'm going to call my function g of x. It cubed the number x. So how does that look? I put it inside of it. I got to draw a cube or what? Like a dice shape? Or is that silly? You know, like that? No.
To the third power.
Nice. There you go. Yeah. But if you'd never heard that before, you know, cube or square, you'd say, what the heck is that? But that's a big part of math, is just all these this terminology, the knowing what they mean by square and cube and whatever other stuff they're trying to tell us. Inverse, now they're throwing new things at us. Yeah. Okay, how about number 9, h? Okay, now we're calling the function h of x. It takes the square root of a number x. All right, well, that's, I guess, pretty straightforward. I know what a square root looks like. Okay. That one's not too bad. All right. How about number 10 then? A function j. Now we're running out of ideas for these names. J of x takes the cube root. That's pretty straightforward. There's not really any other way I could say that. Cube root, that just means instead of a square root, there's usually with a square root, there's an invisible 2 there as the index, they call it. But with a square root, it's so common you don't even need to write that 2. But with any other kind of root, cube root, fourth root, you would write it to specify it's not a 2, it's something else. So you won't see those too often, I think, in your math world. You won't see cube roots of x or anything. Square roots, yeah, you see that, but this not too often, I don't think. But just in case you ever see it, it's good to know how to transform it from words to phrase it, or to math symbols. And then number 11 says, okay, we have capital F. It finds the absolute value of a number x. That's one of those topics we didn't talk about too much, but just knowing what it looks like. The absolute value is just whatever you're taking the absolute value of with vertical bars on either side. And really all it does, we didn't really have a chance to review it last week or the week before. Absolute values just make anything positive. Values make, yeah, a number positive. So this function, no matter what number I give it a positive number, I give it a negative number, it'll spit out what I gave me, but the positive version. So like, for example, the absolute value of 3 is just 3 because it's already positive, but the absolute value of -3 would be +3. It's kind of like how we should be in our lives, you know. Anybody give me any negativity, I just throw positivity back at them, you know. That's some deep stuff, huh? You didn't know math was so deep like that. Anyway, that's pretty much all you need to know about absolute values. It's just whatever it's given, it spits out the positive version of it. Yeah. And then how about number 12 says the function g, capital G, okay. So I'll call it g of x. It finds the reciprocal of a number x. Nice. Okay. Samuel says 1 over x. Yeah, that one's kind of tricky. If you don't remember what the word reciprocal means. Reciprocal. I think we kind of talked about it, how when we're solving equations. Remember how we said if you were solving, like if you had 2/3 x equals 4 or something, and you wanted to solve it, you know, the best way, instead of dividing by that fraction on both sides, the best way is to multiply by the reciprocal, which is just take it and flip it upside down like that. I think that's where we've seen that, maybe, you know, in this class reviewing. Anyway, that's where we've seen it. But reciprocal just means take if it's a whole number, make it a fraction. So I know x is not necessarily a fraction, but if I put it over 1, like we said, any whole number can be made a fraction by putting it over 1. Reciprocal just flips it upside down. So that's a tricky one. You don't see that very often, the word reciprocal, but it's when it pops up, it's just everybody's has to remember it. That's tricky, but we'll see that guy a lot. Yeah, and you've seen it in the homework probably, what that guy's graph looks like and absolute value. So yeah. All right, that's the beginning, the first kind of section of this worksheet. Before we move on, do you have any questions about that, or is that that makes kind of sense? How do you feel about it?
On number 9,
Oh.
up there, is there is the square root right there in front of the X or behind it?
It should be, well, X is inside the square root.
Okay, oh, so there's no 2 there.
Right.
Because the other one has a 3.
You're right.
Number
Technically,
10.
when someone says square root, there should be a 2 there. It should be like that, but we never write that. I guess just because it's so common that there's no need to write the 2. If you see a root with nothing there, then you assume it's just already a 2.
Square root. Okay.
Yeah,
Thank you.
you're welcome. Yeah, thank you for asking. That's a good question. Because it seems strange that, okay, for cube root or fourth root or on, we always write that little number, but why with the square root? Yeah, it's just to remind us that it's technically supposed to be a 2 there, but we never write it. It's just, we're just assume that it's a 2 if there's nothing there, which it seems like would it really be much harder to put a little 2 there every time? Doesn't seem like it, but I guess someone said, I don't feel like writing that 2 anymore, so I'm just going to say when there's no number there, it's a square root. Just for one person probably said, I don't feel like writing that anymore, I guess. But though I think the next section now, we're going to combine more than one operation. So instead of just having a square on X or X multiplied by something, or it might be multiple operations going on at the same time. Those are a little bit easier or harder to deal with, but I think as we build up, it'll make more sense. Some functions combine 2 operations. Okay, for example, here, this function that they wrote here in highlight, h of x is 3 times x minus 4. It has 2 operations. But notice the most important part of this is that the function that first happens to x, because it's in parentheses, the first thing that you're doing to your number x is subtracting 4 from it, because that's kind of immediately happening to x. It's in parentheses. And then once you subtract 4, then you're multiplying the result by 3. So then, so if you break it down, the 2 functions that make up that larger function, it's like h of x has 2 operations, but the 2 basic operations going on in there is 1, I subtract 4 first, and then the second thing I'm doing, if I give it a name, g of x, I'm taking whatever the result is and multiplying by 3. That's what they're saying here. So any function that does more than one thing, you can kind of break it down to 2 functions that just do 1 operation, and somehow they were combined into that one function that was doing more than 1 operation. So what we're going to do is try to break these down and think about what are their parts. If there's a function given to us and it's doing multiple things, can I figure out what those things are? And it's kind of strange to start writing one function as 2 functions separated. But I guess the idea is here, what we're given is probably the composition of 2 functions. Someone took 2 functions like this f and g that we wrote here, and they combined them into one. Instead of one function subtracting 4, the other one multiplying by 3, I want my function to do both of those. Someone already combined them. Now I'm kind of having to go backwards. What were those original functions that were combined into this big one that's doing multiple operations? I think so. That's what we're going to do on these. Is it's kind of like going backwards of what's normally done in composition of functions. Usually, you're given 2 functions and you combine them into one, and that's it. But here they've combined them, and you have to figure out what the original guys were. So for these ones, it says for each function h, give a verbal description of what the function does to a number x. Okay. And then write 2 simpler functions f and g representing the operations in h. Let f represent the operation that is performed first. So I definitely know that there's 2, for each of these, there's 2 things going on. I'm taking it, I guess verbally I'll say it's what's going on first. Am I taking my number x and multiplying by 4 and then adding 1, or am I adding 1 first and then multiplying by 4? What do you think? Let's see, someone said, yeah, you're adding first, huh? That's why they put the addition in the parentheses, so you know that's what you're doing first. Kind of like order of operations, right? Whatever's in parentheses, you're doing first. I take a number x. I'm trying to phrase it the way they did in the previous problems. Add 1, then I do the last operation, the outer one, multiply by 4. So that's what they meant. I think that's what they mean, basically. Something similar to that, at least the phrasing of it. Describe it in words and then say, okay, I'm going to break it down into 2 functions. They said f of x should be your first operation that's happening. And we've already said it verbally, so we know which one's going to go there. And then the g of x should be the second operation. So whatever you decided is the first operation, that's going to go for f. So we said in this case, I'm taking a number x and then I'm adding 1. So that'll be my f. And then the second operation happening was I'm multiplying the number by 4, which it looks weird because it seems like if I were to combine these 2 functions into one, there would be 2 x's running around. But we'll see, either if you've seen the composition section already, or later on in this, we'll probably see it. When you combine these two functions into one, f and g, there'll still only be one x. It's kind of weird, but not to give too much of a preview, but what you'll do is you're going to take the function, sorry, oh no, I did the opposite way. Take the function f, so x plus 1, and I take that whole thing and replace the x here and g with it. So if I want to do the composition, not that that's what they asked us to do, but maybe just seeing it a little bit ahead of time might help when you see it later. When I combine them, I'm going to go 4 times, instead of x, I'm going to put this whole f of x function inside x plus 1. So there won't be 2 x's. Instead of combining the x's, making 2 of them, it'll be one of them is replacing another one. So there's still only one. It's a weird thing to get, I don't know, to wrap my mind around. I had a really hard time with that as a student. It took me a very long time to wrap my mind around that. But I think the more we'll see it, the easier it'll be. They didn't ask us to do that in this problem, but I think just having seen it a little bit now might make it easier when we focus on that portion of composition later. So now they say, okay, we have this another one, 14. Okay, how about as we go, maybe we'll save 14 and 15 for breaking into groups. I hope everybody doesn't mind that. It'll be real quick. How about we'll do this? We did 13 together. Now we'll do 16 together, only because absolute values are kind of weird and they kind of freak me out a little bit. So I want to go over that. And then maybe we'll break into groups and see if we all can agree how to do 14 and 15. And then we'll come back together as a big group. Okay, so on 16, there's 2 operations happening. There's subtraction of 5, and then there's the absolute value. Which one do you think is happening first to x? Is it the absolute value or the subtracting 5?
Absolute value.
Yeah, let's see. X. So I'm taking number x, and I think, well, because the subtraction is inside the absolute value, I think we're wanting to subtract first. Yeah, but if it was the other way around, you know, I think if they had wanted us to take the absolute value first and then subtract, it would have been written like absolute value of x and then minus 5 at the end, you know. So this one, I think because the 5 is included in the absolute value, we're gonna want to subtract 5 first. It's not easy to tell which one's first sometimes, like especially with this one with the absolute value. If we take a number x, subtract 5, then take the absolute value. But it's not obvious which way it is until I think when you see a lot of examples, then it becomes easier. So it sounds like, you know, they said they want not only the verbal description like we did there, but also the function description. F of x, they said, let that be the first operation that's happening. And we said that's where I'm just subtracting 5. And then g is the outer operation. I just put absolute value of x. So there should only be, in f and g, there should only be one operation happening, and that's it. Yeah, and it's like I said, it seems like if I were to combine those two, wouldn't there be 2 x's running around? But really what you'd be doing is taking the x that's in the absolute value function, like taking the x out of the absolute value and throwing this whole thing in there instead. You're replacing that x with x minus 5, and then it would look like the original guy. Anyway, it's weird. It takes some getting used to. Let's see, someone said, does the absolute value words? Yeah, you're right. Jacob asked, that's a good question. The inside, when you have an absolute value, it works, you're right, it works a lot like parentheses with PEMDAS. So I almost feel like they should have said PEMDAS, okay, when they do it, it should be parentheses / absolute value or something, you know, because you're right. If there's absolute values, you should treat it like parentheses. Do what's inside of it first and then operate on what's inside once it's simplified. So you're right, that's a good point. It should be like parentheses / absolute value, but I guess absolute value doesn't happen often enough to put that in PEMDAS, I guess. That's all I can think of. So with that said, okay, I think we're good. We did number 13, 16. So how about we'll break into groups? I know most people hate hearing that, but it does help. Okay, we'll try to see if we can all agree within your group on how 14 and 15 should look. And just keep in mind the phrasing, you know, when you phrase it in words, your answer and someone else's answer don't have to be exactly the same, as long as the order of operations is in the same order. Like in number 14, you're adding 2, multiplying by 5. As long as you agree that you're doing one of those first and the other one second, then it should be, yeah, then you should be right. Maybe you use different words or something, but big, you know, no big deal. Let's see. So how about we'll do group 5, 6 groups, just so there's like 3 people in each one. Okay, we'll break into groups and I'll kind of visit every group and see how you're doing, and then we'll get back together and talk about it.